All right, welcome to Chapter 6, Problem Set 1. First one we're going to be doing today is question 1. Question 1 says, if a box is stationary and the angle between the horizontal and the force F is increased somewhat, do the following quantities increase, decrease, or remain the same? That's a great question. Let's draw the picture real fast. So we're going to have a box on a surface. There's a surface that's put in the box. There's our box. Now, there's a force applied here. Let's do that in green. So the force is applied here, and it's down and to the right. Now, the fact that it's down and to the right, it's going to make some angle with the horizontal. So there's that. And then the angle it makes with the horizontal, we'll call that theta. And so, oh, this is F. All right, so we want to know if the angle between the horizontal and the force is increased somewhat, do the following quantities increase, decrease, or stay the same? Okay, so basically what we're saying is we're going to take this and we're going to increase the angle here. So we're still going to apply with the same force, but the angle itself is going to increase. It's going to go to there. So let's draw the force diagram for the first one, then the force diagram for the second part. So for the first iteration, we know that the Earth is pulling it down. We call that mg. And then there's this force F at whatever angle this is. Now this force is two things at once. It's not only to the right, but it's also down. This is the force in the y direction. This is the force in the x direction. Now, it says it's stationary, which implies that if it's not moving at all, then you have some frictional force here, little f for friction, that's balancing out this applied force here. Now we have to have some normal force. Now, oftentimes, the normal force is equal to the weight, but that is not the case here because you see we have this F in the y direction that's also down, so we have two down forces, and so we actually have to add a little bit extra. So you can see that your normal force here is actually greater than the weight. That's the initial. That goes with this one right here. But what happens if we increase our angle? Okay, we have the same force, but we're going to increase the angle. Let's see what that one looks like. So we still have the same weight. Same mg here. But we're going to change the angle here. So we have the same length, but you can see it's much bigger in terms of the angle. Now, if I look at this, I can see that the F in the y direction has totally increased, and the F in the x direction has totally decreased. Since the F in the x direction has decreased, we can see our friction is a little bit smaller. However, since our F in the y direction is bigger now, our normal force actually had to increase to compensate. So let's see what they're asking for here. They want to know what happened to the F in the x direction. They want to know what happened to the static frictional force. They want to know what happened to the normal force. And they want to know what happened to Fs max. That is the maximum static friction. Well, between our two diagrams, what happened to the F in the x direction? The F in the x direction decreased. The static frictional force, all right, these are both static friction because your object is not going anywhere. So that also decreased. We saw the normal force increased. Now what happens to Fs max? Well, the thing about the Fs maximum, one of the things we know, is that if you want to find the maximum static friction, it's equal to the coefficient of static friction times the normal force, or the way they're writing it here. So these both mean normal force, so depending on here. And since our normal force increased, our maximum also increased. Who said the background? Boom. All right. Next question is, I think it's 3. Let me check my notes. All right, question 3. So we got another drawing here. So we got another block on a surface. Let's get out the surface. There's our surface. We got a pink box this time. We'll do it in red. All right, and there's two forces on this one. We have a force in the down direction and a force to the right. Call this one F1, and we'll call this one F2. All right. Problem says, the horizontal force has a magnitude of 10 newtons is applied to the box, but the box does not slide. Then, as the magnitude of the vertical forces increase from 0, do the following quantities increase, decrease, or stay the same? So basically, you have this force here and it doesn't move, and then we start adding this force to it. Okay. No problem. So your original force diagram would look something like this. So you have the weight of the object. We'll call that mg. And then we have this applied force, which we call F1. And it's not moving, so it's going to be balanced out by the frictional force here, the friction, static friction right there. And then since it's balanced, we can have a sense that the normal force in this case is equal to the weight. That is the original force diagram. Now, what we're going to do is we're going to start applying this F2 here. So I'm still going to have the weight. But as we start applying some more force here, right, some things have to happen to compensate. The main thing that has to happen to compensate is that the normal force has to increase to balance the forces out. And so now we have a much bigger normal force. We still have this F1 to the right, and then we still have the friction to the left. All right, so what are the quantities that they are interested in? Okay. So it wants to know what happens to the static frictional force. It wants to know what happens to the normal force. It wants to know what happens to the Fs maximum. And it says, does the box eventually slide? Okay, let's answer these first. So what happens to static friction? It stays the same. The static frictional force is a result of the applying this F1 here. If you were to increase F1, the static friction would probably increase to compensate until you reach the maximum amount. But here, since you're just pulling up and down, it doesn't change. As we saw, if you apply more downforce, the normal force has to increase to compensate. And the Fs max also increases because we know that the maximum static frictional force is equal to the coefficient of static friction times the normal force. And since the normal force increased, this has to increase also. And D says, does the box move? And the answer is no, because the force that you added, F2, is in the up and down direction, and so there's no way it's going to get it to move side to side. All right, let's look at question 5. Question 5 says, if you press an apple crate against a wall so hard that the crate cannot slide down the wall, what is the direction of static frictional force, normal force, and if you increase your push, what happens to these values and why? Okay, so we're on 5 here, so let me draw the wall. Okay, so there's your wall. Let's get your apple crate out. I don't know why it's an apple crate, but it is. So what you're going to do is you're going to push it against here so hard looks like your arms might be a little long here, but we'll just go for it. So you're going to push it so hard that it doesn't slip. So, well, let's look at the forces. All right, if I draw the force diagram for this bad boy, know that the earth is pulling it down, call that mg. Right, you're pushing it in against the wall. So this is your push, but the wall is pushing it back out. And it's not sliding down. So because the acceleration is 0, the net force is 0, which means the forces have to balance. So whatever downforce you have, you need an up force to go with it. So this is where the problem gets interesting, because oftentimes our normal force is in the up direction, but in this case, it's not. Which way is the wall pushing? The wall is pushing perpendicular this way, so this one is the normal force. And it's not sliding down the wall, so this one is the frictional force. And that is an interesting new type of problem that we're trying to get at here. If you increase your push, what happens to the static friction, the normal force, and the static friction max? All right, so what we're going to do now is we're going to increase the pushing force. And so basically, we're going to say, no, I'm going to push a little bit harder. Well, if you push harder there, what happens to the normal force? The normal force has to increase, okay? But because the weight hasn't increased, the frictional force doesn't have to increase. So we would see that the normal force increases. The static frictional force stays the same, but the Fxs max increases. Because again, the static frictional force maximum value is dependent upon the normal force. And since the normal force increases, the maximum value of the friction increases, which means you could put more stuff in it. So the heavier it is, the harder you would have to push to increase the normal, which increased the maximum friction. Okay, and now we're on to question 13. Question 13 says, a box on a ramp so the angle so that it is an angle theta to the horizontal. As theta is increased from 0 and before the box slips, do the following increase, decrease, or remain the same? All right, it says the component of the gravitational force along the ramp, the magnitude of the static frictional force, okay, let's draw the picture first before we get too excited. So we're going to draw it in 3 parts here. We're going to say, what does this look like if your surface is horizontal? What does it look like if your surface is at a slight angle? Ooh, got a little excited there. No, that's fine with me. Or if your surface is at a steep angle. So let's draw the force diagrams for each of these. Do this one in. Okay. In all 3 of the cases, the Earth pulls it down, straight down. Call that the mg. That's the weight, same thing here. And that doesn't change. But we're going to change, in these 2, we're going to change our angles so that, or our axes, so that we're thinking about an axis along the ramp instead of along the ground. So we're going to break this up into its component parts this way. And then this one is the normal force also. Normal, normal, normal. And it's not moving. So here there's no friction at all. Here there's a little bit of friction to balance that out. And here, since this is so much longer, we have a much longer frictional force here. Okay. So it says we're going to increase the ramp angle. So we could actually just look at these 2, but I wanted to show that the situation is here. Okay. If we increase the ramp angle, so this is the mg here. We call this one the mg x direction, and that's what they're asking for. What happens to the mgx is the first question. Second question is what's happening to the static frictional force. They also want to know what happened to the perpendicular component, that's this one, mgy. And then they want to know what happens to the normal force. And of course, they want to know what happens to the Fs max. Okay, so let's compare these 2. As you increase the ramp angle more, we can see what happens. I mean, look at this is a little short one here. This one is much longer. As you increase the angle, you increase that. So this one increases. Since the friction, right, still the acceleration here is 0, so these forces have to balance. And so you're going to notice that the frictional force has to increase to balance out. So this also increases. But what happens to the mgy? So here you have a nice long MGY here, but we're going to notice that it's getting a little bit shorter, right? So the MGY decreases. And then because that one decreases, the normal force also decreases. And again, because we know that the static friction maximum value is equal to the coefficient of friction times the normal force. Here, we'll do this one. So if this one the normal force goes up, this also has to go up, or if it goes down, it also has to go down. What I like about this problem is, like, if you were to look at the normal force here, this one is the biggest, then this one's a little smaller, and this one's a little smaller. And if you were to continue to increase the ramp, it would get even smaller.